In this video, as well as future videos in this series on operational transconductance amplifiers, we will assume that the device under consideration is the LM13700 and that it is powered on plus and minus 15 volts. Any exceptions to this will be noted wherever it is appropriate. The basic concepts presented will in general be common to essentially any operational transconductance amplifier you happen to be using, but some of the specific values such as voltages and currents may differ somewhat from device to device. When you're using a new device, one with which you're unfamiliar, it is always best to check the data sheet and make sure that you understand what the limitations in particular of the device are, even if the manufacturer claims that it is compatible with a device that you are familiar with. Don't just assume that everything is going to be exactly the same. Let's consider the inputs and the output of the OTA in somewhat more detail. There are two signal inputs, the inverting input, which is a voltage, and the non-inverting input, which also is a voltage. And the thing that we will call Vn is the difference in these two, the non-inverting input voltage minus the inverting input voltage. Now do note, as mentioned in earlier videos, we do need to scale our inputs so that the differential voltage at those two inputs is less than about 10 millivolts. Now this is assuming that you want to maintain a reasonable amount of linearity. If you can stand a little bit more distortion, you can drive it a little bit higher than that. And in fact, I have seen circuits that deliberately use the nonlinearity and deliberately overdrive those inputs. But that's another issue altogether. If you implement linearization using the diode bias input, I sub D, then you can increase your differential input voltage to about 50 millivolts and still maintain the same level of linearity that you had without them at 10 millivolts input. Next, we have the amplifier bias current. Now, one thing of note here is that the absolute maximum current into that input is 2 milliamps. You do not want to exceed that or you will destroy the device. And in fact, as we will see later, you need to be a little bit cautious with this because you can inadvertently destroy the device. Back in the early 70s when I didn't know anything and was trying to figure these things out, I fried quite a few of them because I didn't know what I was doing. So be warned. Something seemingly as innocuous as connecting the amplifier bias current input to ground will destroy the device. We'll see why later. So just be careful. Again, the maximum current you want into that input is 2 milliamps, so you probably want to stay well away from that. So in general, you probably want to keep your amplifier bias current at 1 milliamp or less. Again, as mentioned in an earlier video, if you are not using the linearizing diodes, then the output current is given by 19.2 times IABC times V sub n. Now note that the 19.2 IABC is actually the transconductance G sub m. Next, let's look at the diode bias input, I sub D. Again, the absolute maximum current into this input is 2 milliamps. So in general, typically you'd want that to be about 1 milliamp. Now that's going to be a constant current. You're not going to be changing that. So you're going to set up a current and it's going to remain fixed the entire time, except in very, very rare situations. And typically you would want that to be about 1 milliamp, about half of the absolute maximum value. Again, as already mentioned earlier, this is used to increase the linear range of the input voltage by a factor of about 5, from roughly 10 millivolts up to about 50 millivolts. Now note that when you use the linearizing diodes, in general the output current will be less than the standard output equation 19.2 IABCVN, which is no longer valid. You cannot use that output equation if you're using the linearizing diodes. We'll discuss this in some detail in another video. If you're not using the linearizing diodes, you simply leave that input disconnected. Don't connect it to anything. Don't connect it to ground in particular. Just leave it open. Finally, the output current. We usually will want to convert that current to a voltage. You can use an operational amplifier as a current-controlled voltage source. That's one option. That requires that you add an op-amp to your circuit, of course. You can use the built-in Darlington buffers, but as mentioned in an earlier video, that will introduce about a -1 volt offset in your output voltage. You could use an FET output buffer, but again, that would also introduce a slight negative offset in your output. In the next video, we will consider the signal inputs and the diode bias input in considerably more detail.